So today's lesson is going to be regarding chapter 5, which is all about gases. So you learned in the past chapter that there are four different types or four different states of matter, right? There's solid, liquid, gas, and plasma. And you learned the different properties of the first three, right? Solid, liquid, and gas. But our focus here is going to be on the third one, gases, right? What are the different properties of gases? Okay, so there are four important properties that you need to learn for this chapter, right? The first one is that gases have a variable shape and volume, which makes a lot of sense, right? So if you put a gas, right, in a container, that gas will take the shape of that container, right? Which is actually similar to liquid. When you put a liquid in a soda can, right, or some kind of bottle, it will take the shape of the bottle. But the difference between gases and liquids is that the gas can also take the volume of that container. So if you have let's say oxygen gas in a container, in a 10-gallon container, and then you transfer all that oxygen gas into a 1-gallon container, right? From 10 gallons to 1 gallon. Now that gas, that oxygen gas, now has that 1-gallon container or 1-gallon volume. Okay, the reason for this property is because of properties number 2 and 3, right? Gases can expand and compress. So you can compress gas so that it'll have a 1-gallon volume, or you can expand the gas in order to have a 10-gallon volume. And the fourth important property of gases is that they mix uniformly, right, with other gases in a container. And so if you have, let's say, carbon dioxide, you mix that with oxygen gas, with hydrogen gas, and so on, they will mix uniformly in that container, right? They will be evenly distributed within that container. All right, so again, our focus here is on gases and also pressure, right? Because gases can exert pressure. By definition, pressure is the result of constantly moving gas molecules striking the walls of the container. So if you've taken physics in the past, or maybe chemistry in high school, you learned that pressure by definition is force applied divided by area, right? It's the force exerted or applied per unit area. So I'm just going to write it right here. So pressure is equivalent to the force exerted per unit area. Okay, so the larger the amount of force that's exerted, the greater the pressure, right? Because you're increasing this value right here, right? Because in this equation, pressure is directly proportional to force. So increasing force with increased pressure. With area, it's inversely proportional, right? So if area decreases, then pressure increases, and vice versa. So you increase area, you decrease pressure because you're dividing it by a larger value. So gas pressure is the result of a bunch of gas molecules striking the walls of the container, right, with a specific force in a specific area. So at higher temperature, gas molecules have greater kinetic energy, right? Because kinetic energy is related to temperature. The higher the temperature, the higher the kinetic energy. So at higher temperature, gas molecules have higher kinetic Okay, so also kinetic energy is related to velocity, right? Ke, kinetic energy, is equivalent to 1/2 mv squared, right? Where v is velocity. So at higher temperature, gas molecules move faster. They move a lot faster. And so if they move a lot faster, they will hit that container wall more frequently compared to at lower temperature. And so now you can think of pressure. Okay, so you can think of pressure or gas pressure as frequency of collision. Okay, so I'm going to put frequency of collision here. Okay, I think that's how you spell collision. It might be single S. Oh well. All right, so frequency of collision, right? That's pressure. So if you increase this frequency of collision, you're increasing pressure. So that's what it means. So you might want to remember this for this chapter. So pressure is basically frequency of collision. The higher the frequency of collision, the higher the pressure, okay, and vice versa. So when you look at temperature, the higher the temperature, the gas molecules would move a lot faster. They have higher kinetic, and so they would strike the walls more frequently. And because of that, they have higher frequency of collision, therefore higher pressure. All right, so gas pressure is different from atmospheric pressure. Okay, so atmospheric pressure is the result of the air molecules in the environment around us, right? So there's air molecules all around us, striking with the walls of the room, hitting your skin, colliding with each other, colliding with other molecules in the environment. So this pressure, okay, or this collision between gas molecules and environment and the objects within the vicinity, that causes pressure, and that pressure is called atmospheric pressure. And you can always look up the atmospheric pressure in every city. It's different in every city, right? Because maybe the number of gas molecules is different in, let's say, Pasadena or in Houston or in New York, right? And so, right, so that's the definition of atmospheric pressure. It's the result of the air molecules in the environment colliding with each other. Okay. So there's this guy in the mid 1600s, Evangelista Torricelli. Okay, he invented the barometer, and the barometer is basically a device that measures atmospheric pressure. And this figure over here on the right hand side, this is basically a simple barometer. Okay, it's so this is a glass tube filled with liquid mercury. So they use liquid mercury, as a unit of pressure, right? So there's atmospheric pressure that's exerting onto this liquid mercury, and then it pushes this liquid mercury up. Okay, and the height of this liquid mercury here is measured as the atmospheric pressure. So, for example, if you were to measure the atmospheric pressure right now, and you get this height, right, 29.9 inches of liquid mercury, then that is the pressure in that city, all right, the atmospheric pressure. And you can always convert this to other units of pressure, right? This is 29.9 inches of mercury, and if you convert that to millimeters of mercury, it would be 760 millimeters of mercury. Okay, so again, atmospheric pressure pushes down onto this liquid mercury, causing it to rise up in the tube, and the height in or the height of the liquid mercury is the atmospheric pressure. So atmosphere right here is a unit of pressure, and it has a symbol ATM, right? 1 atmosphere is equivalent to 29.9 inches of mercury, which is also equivalent to 760 millimeters of mercury, or 760 torr, Torr, which is short for torricelli, right? Or we just call it torr, 760 torr. All right, so let's look at the different units of pressure. First, let's define what standard pressure is. Standard pressure is the atmospheric pressure at sea level, 29.9 inches of mercury, or 1 atmosphere. So standard pressure is basically like a frame of reference, right? So that it makes measurement comparisons easier. So like, for example, if you were to measure the height of a mountain, right? How would you compare two mountains? You have to have some kind of frame of reference, and they use sea level as the frame of reference. In pressure, they do the same thing. They use standard pressure, and the standard pressure is 29.9 inches of mercury. Here's a table showing you the different units of pressure. There's atmosphere, right? There's inches of mercury, and the symbol for atmosphere is ATM. Inches of mercury is IN, and then the symbol of mercury, which is Hg. You can also convert that to centimeters of mercury, millimeters of mercury, torr, PSI, which is short for pounds per square inch, and kPa for kilopascals. Okay, let's look at an example here on how to convert one unit of pressure to another. Let's say that we have 26.2 inches of mercury. How do you convert that to atmospheres? ATM, right? So we know that 1 atmosphere is equivalent to 29.9 inches of mercury. So the first thing you want to do here is to write down what's given, right? We're given 26.2 inches of mercury. And now you can use dimensional analysis to solve this problem. So the equivalence factor here is 1 atmosphere equals 29.9 inches of mercury. So you want to multiply this by the equivalence factor by putting inches of mercury at the bottom in the denominator, and then the atmosphere up top, 1 atmosphere. Okay, so now you see how the units would cancel, inches of mercury would cancel, and we get the units that we want, which is atmosphere. So plugging this into the calculator, 26.2 times 1 divided by 29.9, that gives us 0.876 atmosphere. All right, so here's another example. How do you convert 27.5 inches of mercury to PSI, or pounds per square inch? So we know that 14.7 PSI is equivalent to 29.9 inches of mercury. Again, so the first step here is to write down what's given. We have 27.5 inches of mercury, and then you want to use the equivalence factor here. You want to put inches of mercury in the denominator and the PSI up top, which is the unit that we want. Inches of mercury will cancel out, and then you just multiply 27.5 by 14.7 and divide that whole thing by 29.9, and we get 13.5 PSI. All right, so before we get into the math part, first you have to understand the 3 different variables that can affect gas pressure. Okay, so what are these three variables that affect gas pressure? The first one is volume, right? Volume of the container, volume of the gas. Volume of the gas. Second one is temperature, the temperature of the gas. And finally, the number of gas molecules. So all of these three variables can affect the value, the numerical value of pressure. And we're going to take a look at every single one of these in greater detail. Okay, so again, there are three variables that can affect gas pressure. The first one is volume, second one is temperature, and the third one is number of gas molecules. So make sure that you remember all these three variables. The first one that we want to look at is volume. How does volume affect pressure? Okay, remember in the beginning of this lesson, we sort of defined pressure as the force applied per unit area and also the frequency of collision, right? So looking at volume here, how do you think volume will affect pressure? Meaning, if you were to increase the volume of the gas, how would pressure change? Okay, so let's say we have a container here. We have a container right here. Okay, and this container has, let's say, 3 molecules, right? 3 gas molecules. And let's also say that this is, let's say 10 gallons, right? So this is a 10-gallon container. Okay, and the temperature, we're going to keep the temperature and number of molecules constant. So I'm going to put temperature, let's say 298 kelvins. All right. And then we also have a second container here. Okay, I'm going to exaggerate this a little bit. And the temperature is the same. Okay, so we'll put the temperature also at 298 kelvins. And the number of molecules is the same, 3. Okay, so I have 3 gas molecules in here. But now the volume changed, right? So instead of 10, now we have 1 gallon. So how do you think pressure is affected here? So we defined pressure earlier as the frequency of collision. So these molecules, okay, so these gas molecules here inside the container, they're moving around very quickly. Okay, so they're moving in this direction, right? They're moving in random directions and, hitting the container walls, striking the walls of the container. Now imagine the second container, smaller container. These molecules will also hit and collide with the walls of the container, right? And so because we decrease the volume of the container, the frequency of collision here would increase, right? Relative to this container, 10 gallons, because it'll take a shorter distance for these molecules to reach the edge, right? The container, the walls of the container. And so because of this decrease in, because of the increase in frequency of collision, pressure increases. So decreasing volume increases the frequency of collision. And so because of this increase in the frequency of collision, pressure also increases. Okay, so make sure you remember that. Because if we decrease the volume, pressure increases. due to the fact that there was an increase in the frequency of collision. So that's the relationship between volume and pressure. When volume decreases, pressure increases, right? And vice versa. So if you increase volume, pressure decreases. So they are, in other words, inversely proportional to each other. All right, now let's look at variable number 2, which is temperature. How does temperature affect pressure? Okay, if you were to increase temperature, how would that affect pressure? Or if you decrease temperature, how does that affect pressure? Again, we can look at it in terms of containers here with gas molecules. So it says over here, at constant volume and constant number of molecules, or number of moles of molecules. All right, let's say we have 2 containers here, okay, with, let's say, 3 gas molecules again. Okay, 2 containers, same volume, same number of molecules. The only difference here is temperature. All right, so the temperature for this first one here on the left, let's say 100 degrees Celsius or 100 Kelvins. And on the right hand side, temperature is tripled, 300 Kelvins. All right, so again, you always want to think of frequency of collision here. How is this going to affect this frequency of collision? All right, so again, you learned in the past that at higher temperature, there's higher kinetic energy. And if you have higher kinetic energy, the molecules, the gas molecules, have a higher velocity. They move a lot faster. And so because these molecules here are moving a lot faster compared to at 100 kelvins, the frequency of collision is also higher. Okay, so the frequency of collision here is higher. Frequency of collision. Okay, and because the frequency of collision here is higher, pressure is also higher. All right, so the relationship between pressure and temperature is directly related. Okay, so they are directly proportional to each other. The higher the temperature, the greater the pressure. The lower the temperature, the lower the pressure. And the third variable here is the number of molecules. And how would the number of moles or number of molecules affect gas pressure? And this one, we're looking at the other 2 variables remaining constant, right? Not changing. So this is at constant temperature and volume. So again, if we have, let's say, 2 containers, right, with the same volume and temperature, but the only difference here is the number of molecules. So I'm going to add a lot more molecules here on the right hand side, the right container. Okay, so now looking at, okay, so this is at same temperature and volume. So because we're looking at the number of molecules here, you can see that this container would result in higher frequency of collision. Okay, and because the second container contains more molecules, it has higher frequency of collision, higher pressure. So this one has higher or greater pressure. So again, that's the relationship between the number of molecules and pressure. So you increase the number of molecules in the container, you're increasing the pressure as well. All right, so let's look at some practice problems here. State whether the pressure of a gas in a sealed container increases or decreases with each of the following changes. The first one here is regarding volume. Second one is about temperature, and the other one is moles of gas or the number of molecules of gas. So the volume changes from 250 liters to 500 liters, right? So looking at the first problem here, you can see that there was an increase in volume. All right, so let's look at some practice problems here. State whether the pressure of a gas in a sealed container increases or decreases with each of the following changes. So here we have volume changing from 250 liters to 500 liters. How would that affect pressure of the gas within the container? So what you can do here is to look at how the volume changed, right? So this is a decrease in volume. So what happens when volume decreases? How would that affect pressure? Well, volume and pressure are inversely related, right? Inversely proportional. So decreasing volume would increase the pressure. All right, the second one here is temperature. How would that affect pressure? So for this one, temperature changes from 20 degrees Celsius to negative 20 degrees Celsius. So this is a drop in temperature. So temperature decreased, right? How would that affect pressure? Temperature and pressure are directly related, directly proportional, and so pressure would decrease here. And finally, moles of gas changes from 1 mole to 3 moles. So this one is an increase. So this is an increase in number of moles. And number of moles is a symbol N. So if there was an increase in the number of moles, pressure also increases. All right, so in this chapter, you're going to learn about several different gas laws. All right, so there's 2, 4, 6 different gas laws here. There's Boyle's law, Charles's law, Gay Lussac's law, Avogadro's law, combined gas law, and ideal gas law. So we're going to take a look at every single one of these in greater detail. All right, so the first one is related to Boyle's law. Right, so Robert Boyle was able to prove or show the relationship between volume and pressure. Right, so he used this J tube here. Okay, this little device. So it's basically a glass tube with a shape of similar to the letter J. Right, so it's a J tube device. So what he did was he found that the volume of air decreased as he added more mercury. Okay, so when he doubled the pressure at constant temperature, the volume was reduced to half. Okay, so let me show you how to read a J tube real quick. So this is a J tube. So inside here is liquid mercury. Okay, so we have liquid mercury here. And if the level of liquid mercury is the same on both sides of the J tube, then the pressure of the trapped air right here. So the pressure of air is equal to the pressure of the atmosphere. Okay, so because the pressure of the atmosphere is 760 millimeter mercury, then the pressure of the trapped air here is also 760 millimeter mercury. So now when Robert increased the pressure, he did so by adding more liquid mercury into the J tube. So he added 760 millimeter mercury. All right, so now you have this height difference here, which is 760 liquid mercury. So now what would be, how would you calculate the pressure of the trapped air here? So the pressure of this trapped air is now equivalent to the pressure of the atmosphere, okay, plus the pressure applied by the liquid mercury. So this is, I'm just going to put height of the liquid mercury here. Height. So in that case, all we have to do is add 760 right, plus another 760 coming from the atmosphere. And that gives us 1,520 millimeter mercury. All right, let's do a little practice here and determine the pressure of the gas. All right, looking at the first one here, we have a J tube, right? And the level is the same, right? The level of the liquid mercury is the same. So the pressure of the trapped gas should be equivalent to the pressure of the atmosphere. So in that case, the pressure of gas here is 760 millimeter mercury. For the second J tube here, we have, again, the pressure of the atmosphere here, which is 760 millimeter mercury. And then now, we also have this height of mercury right here, which is equivalent to 760 millimeter mercury. So to get the pressure of this gas, all you have to do is add the height of the gas or the liquid mercury. So P gas is equal to pH, the height, plus P atmosphere. Okay, so in that case, we have 760 plus 760, which is equivalent to 1,520 millimeter mercury. Okay. And the third one here, same concept. So it's basically the height of the mercury plus the atmospheric pressure. So in that case, 1520 plus 760. And that gives us 2,280 millimeter mercury. So that's the pressure of the gas that's trapped in the tube. All right, so let's look at Boyle's law. right? So Boyle's law basically states that the volume of the gas is inversely proportional to the pressure of the gas at constant temperature. So mathematically, this is the relationship between pressure and volume. So again, this has to be at constant temperature and constant number of moles. Okay, so you're leaving two of the variables constant. One is the temperature and the other one is number of moles. So P1 V1 equals P2 V2, right? Initial pressure times initial volume is equal to the initial or the final pressure times the final volume. So this is the mathematical relationship between volume and pressure. So let's look at this one example here. A 3.50 liter sample of methane gas exerts a pressure of 1,550 millimeter mercury. What is the final pressure if the volume changes to 7 liters? All right, so this is what's given, right? We were given the initial volume and the initial pressure. So we have 3.5 liters of the sample at 1,550 millimeter mercury, and we're given the final volume of 7 liters, right? And we're trying to find what the final pressure is. So you can kind of use the concept here, right? So you have an increase in volume from 3.5 to 7 liters, and you know that volume and pressure are inversely proportional. If there was an increase in volume, there would be a decrease in pressure. So you can kind of predict that the value of the final pressure would be lower than the initial pressure. And so, because volume increase or doubled, then you can kind of guess that the final pressure would decrease by half. So this is the equation that you're going to need, and we're going to use basic algebra to isolate P2, right? So we're trying to find what this is. Okay, so in order to do that, all you have to do is divide both sides by V2, right? So we want to isolate P2 by itself. So here you can see that V2 will cancel out, and you're left with the final pressure. So then P2 is equivalent to P1 times V1 divided by V2. All right. And all you have to do now is plug in the numbers. So we have P1, which is 1,550 millimeter mercury. Okay. And you're going to multiply this by the volume, which is 3.5 liters, divided by the second volume, which is 7 liters. All right, so you can see how the units cancel out, and you're left with the unit millimeter mercury. So here we get 775 millimeter of mercury. All right, here's another example. A balloon has a volume of 2.5 liters at a pressure of 1 atmosphere. If the pressure around the balloon is decreased to 0.80 atmosphere, what is the new volume of the balloon? So again, this is what's given. And we want to calculate the final volume. So again, looking at pressure, right? How did the pressure change? So there was a decrease in pressure from 1 to 0.8. And we know that pressure is inversely proportional to volume, so decreasing pressure would result in the increase in volume. So you would expect V2 to be a larger value than V1. All right, so the equation that we will need here is the Boyle's law equation. All right, so we have P1 V1 equals P2 V2. All right, and we want to isolate V2 by itself. So what we can do is divide both sides by P2. And you can see how the units would cancel out here. And now we have V2 by itself. V2 equals P1 times V1 divided by P2. All right, and all you have to do now is plug in the numbers. So we have pressure 1, which is 1 atmosphere. And you multiply this by volume 1, which is 2.5 liters. And divide this entire thing by P2, which is 0.80 atmosphere. Okay, so atmospheres cancel out. And what's left is the unit for volume. So we get 3.125 liter. And you can always apply sig figs if you want. In this case, there should only be 2 significant figures. All right, so the next law after Boyle's law is Charles's law. And Charles's law basically relates volume and temperature. And according to his law, they are related. They are directly related, volume and temperature. So he discovered that the volume of a gas is directly proportional to the temperature in Kelvin. Okay, so the unit has to be in Kelvin. So he basically looked at a specific gas, right? A certain gas with different number of moles, right? He used number of moles of 1, 0.5, and 0.25, and holding the pressure constant. And he basically observed the same thing for every single one of them, right? Linear relationship between temperature and volume. So if you look here, the volume decreases as the temperature decreases. So they are directly related, right? So for example, if you look at the volume, this data right here, right? So the volume is 50 liters at what temperature? At 700 or 673 kelvins, right? So according to Charles, okay, decreasing the volume would also decrease the temperature, or decreasing the temperature would decrease the volume. So if we decrease the temperature by 2 or by half, 673 divided by 2, we get 336. So it's probably roughly right here. Right, this is 336 kelvins. And you would expect the volume to decrease by half. And as you can see, when you decrease the temperature by half, the volume also decreased by half. And this right here is the mathematical relationship between volume and temperature. So initial volume divided by the initial temperature is equivalent to the final volume divided by final temperature. And every time you're working with temperature, you have to convert the unit to kelvins. So for example, if you were given degrees Celsius, you want to make sure that you change that or you convert that to Kelvin temperature, because these equations are formulated based on the fact that they use the absolute scale, which is kelvins. And one other important discovery here is the absolute temperature, or absolute zero, right? So Charles basically looked at several data points, right? Several data points here. And at the time, he wasn't able to do an experiments below 0 degrees Celsius. And but he noticed that these data points can be connected, right, via a straight line. Okay, and he can extrapolate this line all the way to the x-axis. Okay, he was able to extrapolate that line all the way to the x-axis, and that's when he determined that this is the coldest temperature possible, okay, which is absolute zero Kelvin. The reason why is because there's no way that you can get negative volume at colder temperature. And so that's basically the limit, 0 Kelvin, the coldest temperature possible. Here's an illustration of Charles's law, right? How volume and temperature are related. So here's a hot air balloon. Let's see. So you can see that when the air molecules in this balloon is heated, in other words, you're increasing the temperature, you'd also be increasing the volume of the balloon, right? And that's why the balloon expands. A simpler illustration of Charles's law is shown here, where you have a simple balloon, and this balloon contains air molecules inside, right? Let's say that this balloon right here is at room temperature, okay? And you poured liquid nitrogen onto this balloon. What happens is that the temperature of the air molecules inside the balloon decreases. And because of that decrease in temperature, the volume also decreases. So that's the relationship between volume and temperature. All right, let's look at an example here. A 132-liter helium balloon is heated from 20 degrees Celsius to 40 degrees Celsius. What is the final volume at constant pressure? All right, so we're given temperature in degrees Celsius. And so the first step here is to convert degrees Celsius to kelvins. And converting degrees Celsius to kelvins is pretty simple. All you have to do is add the number 273. So these are the values, right? We have the initial temperature of 20 degrees Celsius. Converting that to kelvins gives us 293 kelvins. And for the final temperature of 40 degrees Celsius, that converts to 313 kelvins. All right, so this is what we have. And we're trying to determine the final volume, right? What is the final volume at constant pressure? And the equation right here is the one that we need. And we're trying to calculate final volume. So all you have to do is move final temperature over here, cross multiply, and that isolates V2. So now volume 2 is equal to V1 times V2 divided by T1. And all you have to do now is plug in the numbers. So we have volume 1, which is 132 liters, multiplied by final temperature, which is 313 kelvins, divided by initial temperature, which is 293 kelvins. Alright, so you can see that kelvins would cancel out, leaving you with the unit that you want, which is in liters. And that gives us 141 liters. All right, here's another example. A gas occupies a volume of 15.2 liters at 25 degrees Celsius. At what temperature would this gas expand to a volume of 30.4 liters? Express your answer in both kelvins and degrees Celsius. All right, so this is what's given. We have the initial volume of 15.2 liters at temperature of 25 degrees Celsius, so we must convert this to kelvins first. And then we're given the final volume of the gas, which is 30.4 liters. Okay, and so we're trying to find the final temperature. So converting the temperature first to kelvins gives us 298 kelvins. And again, this is the equation that you're going to need. And we're trying to isolate T2 this time. Okay, so to isolate T2, you can cross multiply. Okay. So this gives us V1 times T2 equals V2 times T1. Okay, and we can try to isolate T2 by itself, because that's what we're trying to find, by dividing both sides by V1. Okay, so V1 would cancel out, leaving you with T2. So this is the equation that we get, and all you have to do now is plug in the numbers. So we have V2, which is 30.4 liters. And multiply that by initial temperature, which is 298 kelvins. And divide this entire thing by initial volume, which is 15.2. All right, liters would cancel out. And we get 596 kelvins. All right, and so to convert this to degrees Celsius, all you have to do is subtract 273. Right, so 596 minus 273. And we get 323 degrees Celsius. All right, and the third law here is Gay Lussac's law, which basically states that the pressure of the gas is directly proportional to the temperature. So if you were to increase pressure, or if you were to increase temperature, pressure also increases, and vice versa. And the mathematical relationship is shown here. So initial pressure divided by initial temperature is equivalent to the final pressure divided by final temperature. So again, we're dealing with temperatures here, and so it's important that you convert the units to kelvins first. All right, this illustrates Gay Lussac's law. So if you were to increase the temperature in this gas cylinder, right, from 300 kelvins to 600 kelvins, then you would expect the pressure to rise as well, to increase, to double. So you double the temperature, you would also double the pressure. So here's an example. A steel container of nitrous oxide at 10.4 atmosphere is cooled from 33 degrees Celsius to negative 28 degrees Celsius. What is the final pressure at constant volume? So it's asking you for the final pressure. So you're given the initial pressure in atmosphere, you're given the initial temperature, 33 degrees Celsius, and the final temperature is negative 28 degrees Celsius. So you would expect the pressure to decrease as well because you're decreasing temperature to negative 28 degrees Celsius. So this is what's given, and you want to convert the temperatures to kelvins first. All right. So we want to calculate P2. This is the equation that we need. And we want to find P2. All right, so all you have to do is cross multiply, move T2 to the other side, and that basically isolates P2. So P2, final pressure, is equal to the initial pressure times the final temperature divided by initial temperature. And all you have to do now is plug in the numbers. We have initial pressure of 10.4 atmosphere. And you want to multiply this by the final temperature, which is 245 kelvins, divided by initial temperature of 306 kelvins. All right, the units kelvins cancel out, and you're left with pressure in atmosphere. So P2 is equivalent to 8.33 atmosphere. All right, so far we've looked at three different gas laws, right? Boyle's law, Charles's law, and Gay Lussac's law. The fourth one here is Avogadro's law. So now this one relates the number of molecules with volume, right? So how are volume and number of moles related? So according to Avogadro's law, the volume is directly proportional to the number of gas molecules. So if you were to increase the number of gas molecules, you're also increasing the volume because the pressure and temperature have to remain constant. So let me show you that visually. So again, let's say we have two containers right here. Okay, two containers. Well, let's see. Okay, so let's say we have two containers here. And in the first container, let's say we have three gas molecules. Okay, and on the second container, we have a bunch of molecules here. Okay, so that's a lot of gas molecules in this container. So according to Avogadro's law, volume is directly proportional to the number of gas molecules at constant pressure and temperature. So let's say that we're going to give this a pressure of 1 atmosphere for both. Right? We're going to keep this constant, not changing. Same thing with temperature. Let's say 298 kelvins. So according to what you learned regarding volume and pressure, right? So you can see that the pressure in this second container would be a lot higher compared to the pressure in the first container, right? Because you have a lot of gas molecules here that are colliding with each other, colliding with the container walls, causing a rise in pressure. And so what would happen if we kept the pressure constant, right? What happens if we prevent the rise or the increase in pressure in the second container? Well, according to Avogadro's law, volume has to expand proportionally to the number of molecules. Okay? So in order for that to happen, the second container has to expand dramatically in order to compensate for that increase in pressure. Right? So when you increase this pressure, when you expand the volume, then these molecules are basically farther apart, right? Decreasing the pressure. So that's what Avogadro's law is saying, that if you kept the pressure constant as well as the temperature, then the increase in number of molecules results in the increase in volume. So they are directly proportional to each other. All right, and you can see that graphically here. So as the number of moles increases from left to right, the volume of the gas also increases from bottom to top. Okay, so let's say that, let's pick a point here. Let's say about 0.25. Right here. Right, so the volume is roughly 5 liters. So you would expect the volume of, let's say you increase the number of moles by 2, right? You're doubling it from 0.2 to 0.4, 0.45 or something like that. Then you would expect the volume to double as well. Okay, from 5 liters to 10 liters. So the volume of a gas sample increases linearly with the number of moles in the sample. Avogadro's law also states that when the amount of gas in the sample increases at constant temperature and pressure, its volume increases in direct proportion because the greater number of gas particles fill more space. And the mathematical relationship between the two variables, volume and number of moles, is expressed in this formula here. So volume, the initial volume of the gas divided by the initial number of moles of the gas is equivalent to the final volume divided by the final number of moles. All right, let's take a look at this example here at STP. So STP stands for standard temperature and pressure. So standard temperature, if you remember from the beginning of the lecture, standard pressure is 29.9 inches mercury or 760 millimeter mercury. And standard temperature is 0 degrees Celsius or 273 kelvins. So that's standard temperature and pressure. 1 mole of gas occupies a volume of 22.4 liters. At the same temperature and pressure, what volume does 5 moles of gas occupy? So you're keeping the temperature and pressure constant because it tells you that it's at the same temperature and pressure. So you're only really looking at the number of moles of gas and the volume and how that changes. So it tells you that the volume or that the number of moles of gas increase from 1 mole to 5 moles. What would be the volume of the gas, the final volume? So because you increase the number of moles of gas 5 times, you would expect the volume of the gas to increase 5 times as well. And you can prove that mathematically using that equation. V1 over N1 equals V2 over N2. Okay, so using this equation to find basically V2, right? So we can isolate V2 by moving N2 to the other side. So now V2 is equal to V1 times N2 divided by N1. Okay, and then all you have to do now is plug in the numbers. So our initial volume was 22.4 liters. Multiply this by N2, which is 5 moles, divided by the initial number of moles, which is 1 mole. All right, so you can see how the moles would cancel each other out. And that gives us 112 liters. All right, so when we study gases, there's a lot of variables involved. It's not just one variable or two variables. There are multiple different variables. And so we have to have a more accurate equation to study the gases, the behavior of gases. So if we combine all the 3 gas laws that we just looked at, the first 3 gas laws, right? Boyle's law, Charles's law, and Gay Lussac's law, what we get is the combined gas law. Okay, so if you look at the first one here, if you look at the numerator, the numerator, P1 V1 equals P2 V2. That's Boyle's law. That's Boyle's law. And then Charles's law, it's V1 over T1 equals V2 over T2. That's Charles's law. And Gay Lussac's law is pressure and temperature, P1 over T1 equals P2 over T2. So when you combine all 3 gas laws, what we get is this equation, which is the combined gas law equation. So how do we use this equation? Let's look at an example. A gas takes up a volume of 17 liters, has a pressure of 2.30 atmospheres, and a temperature of 299 kelvins. If the temperature was raised to 350 kelvins and the pressure was lowered to 1.5 atmospheres, what is the new volume of the gas? So we're going to use this equation, the combined gas law equation, and we're going to isolate V2, right? The final volume. What is the final volume? V2. So we're going to rearrange the equation so that we're going to rearrange the equation in order to get V2 by itself. Okay, and so all you have to do now is plug in the numbers, right? P1, the first pressure 2.30 times the initial volume 17 times the final temperature, which is 350 kelvins, divided by 299K times 1.5 atmosphere. Okay, and you get 30.5 liters. All right, let's take a look at another example here. A gas with a temperature of 280 kelvins, a pressure of 200 kilopascals, and a volume of 25.8 liters is compressed to 15.8 liters, causing the pressure to increase to 350 kilopascals. What is the temperature of the gas under the new conditions? So again, it's going to be a little bit more difficult to just use concepts, right? It's very difficult to conceptualize this and imagine it because now you have multiple different variables. So it's important to use mathematics here to see how things would change depending on the conditions. And so these are the given conditions here. We have initial temperature of 280. We have an initial pressure of 200 kilopascals, initial volume of 25.8. And then it says that you compress this, so you change the volume to 15.8, so you compress it, it decreases to 15.8, increasing the pressure to 350 kilopascals. What is the temperature of the gas under the new conditions? All right, so all we have to do is use the combined gas law equation to calculate for the final temperature. Right, so this is the equation for the combined gas law, and we want to solve for the final temperature. Okay, so what we can do here is to cross multiply. Okay, so we're going to cross multiply here, and we get P1 times V1 times T2 equals P2 V2 times T1. Right, so that's the result of cross multiplication. And now we want to isolate T2 by itself, so we can divide both sides by P1 V1. Okay, so I'm going to divide both sides by P1 V1. So you see how P1 would cancel with P1, V1 here would cancel, and now you're left with the equation for T2. So here's the equation for T2. And all you have to do now is plug in the numbers. So we have the final pressure of 350 kilopascals multiplied by final volume of 15.8 liters times initial temperature of 280 kelvins. And you're going to divide this whole thing by initial pressure, which is 200 kPa, times initial volume of 25.8 liters. All right, so kPa would cancel out, liters would cancel, leaving you with the unit in kelvins. And this gives us roughly 300 kelvins. All right, and I think this is second to the last gas law that we're going to cover. It's called ideal gas law. And ideal gas law is more of a complete gas law compared to the combined gas law, because now you're looking at all three variables here: volume, temperature, and number of moles. So when we combine all three variables and how these three variables affect pressure, we get the ideal gas law equation, right? So here we have pressure, volume, number of moles, and temperature. R here is what they call the ideal gas constant, which is the proportionality constant. So this number never changes, right? And the value of R, the ideal gas constant, is this right here. It's 0.08206 with these units. It's liters, atmospheres divided by mole Kelvin, right? So these are the units of the other variables. So we have pressure in atmosphere, which matches this one, volume in liters, number of moles, and temperature in kelvins. So this is the ideal gas law equation. You might want to remember this: PV equals nRT. All right, so let's apply this equation in this example problem here. Calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 kelvins. All right, so we're given the number of moles, we're given the pressure, we're given the temperature, and we have to find volume. Okay, we can use the ideal gas law equation, which is PV equals nRT. All right, so PV equals nRT. And we want to isolate V by itself, and we can do so by dividing both sides by P. All right, you can see how P would cancel, leaving you with the unit, or leaving you with the formula for volume. All right, so all you have to do now is plug in the numbers. So we have the number of moles, which is 0.845. And you multiply this by the ideal gas constant, which is 0.08206. Multiply this by temperature, which is 315 kelvins, and divide this whole thing by pressure, which is 1.37 atmosphere. So now you can see how the units are canceling out. So you have moles here, mole here, atmosphere and atmosphere, kelvins and kelvins. All right, so you're left with unit of volume, which is liters. And we get a volume of 15.9 liters. All right, so one more example regarding ideal gas law. At what temperature does 1.20 moles of hydrogen gas occupy a volume of 28.1 liters at a pressure of 121 kilopascals? All right, so we're given the number of moles, the volume, the pressure, and we know the ideal gas constant, and we have to find the temperature. All right, so these are the things that are given, and we have to find a temperature in kelvins. We can use this ideal gas law equation, PV equals nRT, but the problem here is that this is pressure in kilopascals, and so we would have to convert this to atmospheres first, right? So we're going to convert this to atmospheres. So we have 121 kilopascals so 1 atmosphere is equivalent to 101.325 kilopascals. All right, so kPa would cancel out. And we get 1.19 atmosphere. All right, so now we're trying to find temperature. And we can use this equation here, PV equals nRT, to get temperature. So we can just divide both sides by nR so that we can isolate temperature by itself. So nR would cancel out, leaving you with the formula for temperature. So temperature equals PV divided by nR. All right, so all you have to do now is plug in the numbers. So we have the pressure in atmosphere, which is 1.19 atm. And you multiply this by volume, which is 28.1 liters, divided by the number of moles, which is 1.20, times ideal gas constant, which is 0.08206, and the units. All right, so we have atmosphere will cancel out, liters, moles, and then you're left with the unit for temperature, which is kelvins. All right, plug this into the calculator and we get 339, so we can just round this to 340 kelvins. All right, so the last topic here is going to be regarding gas mixtures. So there's a lot of gas samples that are not pure, meaning they don't contain just one pure sample. They're actually mixtures of different gases, right? For example, air. So when you take a sample of air, it contains a mixture of different gases such as nitrogen gas, oxygen gas, carbon dioxide, maybe small traces of argon, maybe benzene, some toxic gases. Nitrogen, for instance, air contains 78% of nitrogen gas, 21% of oxygen gas, and 0.9% of argon, and so on and so forth. So when we're dealing with gas mixtures, how do we solve, or how do we calculate pressure? Right? How do we calculate the total pressure, or maybe the individual pressure of the gases within the same sample? So the pressure of a single gas in a mixture of gases is called partial pressure. Okay, so this is the pressure of an individual gas in a mixture. Okay, partial pressure. We can calculate the partial pressure of a gas if we know two things. The first one is fraction of the mixture it composes and the total pressure, or we know the number of moles of the gas in a container of known volume and temperature. The sum of the partial pressures of all the gases in the container equals the total pressure. And this is called Dalton's law of partial pressures. And so we can use this equation here, or this formula, to find the total pressure, right? So if you have, let's say, the partial pressure of oxygen gas, pressure of nitrogen gas, carbon dioxide, argon, and all the other trace gases, add them all together and you get the total pressure of air. So partial pressure can be calculated using this equation at the bottom. So the pressure due to any individual component in a gas mixture is its partial pressure. And we give it a symbol P sub n for partial pressure. We can calculate partial pressure from the ideal gas law by using this equation shown below. So we're assuming that each gas component acts independently from one another. So if we have a multi-component gas mixture, we can calculate the partial pressure of each component from the ideal gas law and the number of moles of that component using these equations below. Okay, so for example, if we have gas A, gas B, and gas C, right, all in one container, then we can calculate the individual pressure of each gas using these equations, right? So, and this is based off of the ideal gas law equation, right? PV equals nRT. And the only difference here, so they all share the same temperature, the same volume, right? The only difference here is the amount of moles, the number of moles of each type of gas. So the pressure of gas A is equivalent to the number of moles of gas A times RT divided by V. Okay? The individual partial pressure of gas B is equivalent to the number of moles of B times RT divided by V. Same thing with P for the gas C. All right, and once you determine the individual partial pressures of each gases, then you can determine the total pressure of that mixture by simply adding them all together using this equation. All right, so let's look at a simple example here. So let's say you have a sample of a mixture of gases, right? And that mixture contains these four different noble gases: helium, neon, argon, and krypton. And you know the partial pressures of each gas. You know the partial pressure of helium, which is 125 millimeter mercury, partial pressure of argon, neon, and krypton. What would be the total pressure of the sample in millimeter mercury? Well, all you have to do is add them all up. All right, so simply add up all the individual partial pressures. using this equation. So the partial pressure of helium plus that of neon, argon, and krypton gives us the total pressure. And that would give us 345 millimeter mercury. So this is a simple type of Dalton's law problem. Let's look at a more challenging one in the next slide. All right, so here we have a mixture of gases containing nitrogen gas, oxygen gas, and carbon dioxide. Okay, so 3 different gases. If a 40-liter cylinder is filled with 5 moles of nitrogen gas, 2 moles of oxygen gas, and 3 moles of carbon dioxide gas at a temperature of 400 kelvins, what is the pressure inside the cylinder? So in other words, what is the total pressure inside the cylinder? So we are given this information, right? So we know the volume, the total volume of the container. We know the temperature inside the container, and we also know the ideal gas constant. We are also given the number of moles of the gases. So we can easily calculate this. We can easily determine the total pressure by first determining the individual partial pressures of the gases and then adding them all up together to get the total pressure. So these are the equations that we will need. All right, so we can find the partial pressure of we can determine the partial pressure of nitrogen gas, okay, the partial pressure of oxygen gas, and the partial pressure of the carbon dioxide gas, right, using these equations. So for nitrogen gas, that would be the number of moles of nitrogen gas times RT divided by V. And we can do the same thing for oxygen gas, right? Number of moles of oxygen gas times RT divided by V. Number of moles of carbon dioxide gas times RT divided by V. All right. So all you have to do now is plug in the numbers. We know the number of moles of nitrogen gas, which is 5 moles. All right, so that's 5 moles times ideal gas constant. I'm just going to leave it as R here, times the temperature of 400 kelvins divided by volume, which is 40 liters. All right, we can do the same thing for the other 2 gases. The number of moles of oxygen gas is 2 times RT divided by V. And then for carbon dioxide, that's 3 moles times RT divided by V. All right, so now we can calculate the number of the partial pressure of each of these individual gases. So for nitrogen gas, 5 times the ideal gas constant, 0.08206, times 400 divided by 40, and we get 4.103. And this is in atmosphere. Okay, for oxygen gas, 2 times 0.08206 times 400 divided by 40, and we get 1.64. ATM. And the last one, 3 times 0.08206 times 400 divided by 40, and we get 2.462. All right, so these are the individual partial pressures of the gases. And then to get the total, we just add them all up. So P total equals 8.21. So I'm just going to round this to 8.21 atmosphere.